Today we'll discuss about the design of furnace. So in this lecture we are going to use some standard method for the designing of radiant section. So this is a method Hotel-Wilson model on the method for the radiant section of the furnace designing. So for that thing it's simply a equation. So that equation you can use to find out the some important aspects in the radiant section, and that is basically R. And what is R? This is a radiant heat absorption, and that equation is that can be calculated with the help of this equation. In this one there are different parameters, so let us take one by one. R is the percentage of heat absorbed in the radiant section. So this is the first one that we want to calculate. We have to find out. It is given in the percentage value. G, the second parameter, that is this G. G is the air fuel ratio on the weight basis that is given into the furnace. Then we have a one part, that is the alpha. This alpha is a factor to convert the actual exposed surface to the cold surface, and normally these are the values 0.986 for the 2 row at spacing of 2 OD. Either it can be given in the question or it can be taken as 0.986. Sometimes it is given in the question. Now the next parameter is a Q. This Q is simply the heat, and that is supplied, that is given by the fuel into the furnace. And come to the value of S. S is a factor that depends on the value of Q, and especially the unit of the Q. If the Q is calculated in the kilojoules per hour, then S value will be taken as 14,200, and also the area should be given in the meter square. Area, this A nu is the area, so you have to calculate the area also, and that area should be given in meter square. The second possible configuration and the value of the S depends on if the Q is given in the BTU per hour and the area is given in the feet square. Then the S value is taken as a 4,200. Third possibility, if the Q is given the kilocalorie per hour, area is given in the meter square, then the S value will be 6930. So it depends on the nature of the value of Q. And so Q, that the last, that is alpha nu, that is the area of the wall having tubes in front of it. That is a refractory wall that you have to calculate the area of that one also. So if you calculate, if all these values are known, you can find out the value of R. That is a simple method to find out. That's one equation, and that equation is known as a Hotel-Wilson model or the Hotel-Wilson method. We can go for even calculations also, but after the radiant section designing, we can go for the convection section designing also. But the convection section is basically very similar to the any designing that is carried out in the convection section. For example, the heat exchanger, normally they are using different equations for the convection sections. So convection section very resembles any other heat exchanging system. Unlike the radiant coefficient, convection coefficient depends upon the many factors. You can use the different equations. So our main concern is not about the convection section design. In the furnace, especially the radiant section design, is a much more concerned. So we are again returning back into the radiant section. Let us take one example of the radiant section using the Hotel-Wilson model. So this is the equation, that is the problem that is given here. Suppose we want to heat a petroleum stock, and that is given here. The rate of the petroleum stock is 12,000 barrels per hour, with the specific gravity of that material is also given, and it has to be passed through the basically the furnaces at the radiant section of the box, and at 220 degrees Celsius. The exchanger is designed, the furnace is designed to burn 3,500 kg per hour of refinery of gases as a fuel. So we are using the refinery of gas as a fuel, and the net heating value of that fuel is given here also, that is a 47.46 into 3 kilojoules per kg, means 1 kg of the refinery of gases burned 47.46 into 3 kilojoules of the energy will be liberated. The radiant section contains 150 square meters of projected area of one row of tubes. So that is a given for the one row of tubes. This is a projected area, and these are the dimensions of the one tube, that is a 10.5 centimeter of the diameter, 12 meters long, and it had the space of 2 OD. So these are required things basically. What is to find out the outlet temperature of the petroleum stock, means what happen if the refinery of gases are burned, combustions taking place in the furnaces. Obviously the heat will be absorbed by the petroleum stock, and the temperature of that will not be same as 220, but it will be raised. So we have to find out how much temperature will be raised because of that heat liberated in the radiant section. So we have to see all the parameters. So alpha is given here 0.88, air fuel ratio is given here, specific heat of stock is given here. So almost every parameter is given. You have to simply put all these values in this equation. One thing is missing here. If you see, G is given here, S value depends on Q value, and Q is given here, alpha is given here. The only left value is the A. So in fact all the calculations are based on the calculations of A. Now come to the solution step. In the solution, air fuel ratio G is given as 25 value, alpha value it is given as 0.88 value. Okay, then S value is taken as 14,200. Why? Because the value of G is given in kilojoules and area in the meter square. So if we take the Q in kilojoules per hour and area in meter, so obviously we can take the value of S as 14,200. That's okay. Now Q, that how to calculate the Q value, that is the total heat liberated by the refinery of gases. It's very simple, total amount and flow rate. So we know that this is the 10 to the power 3, it should be 10 to the power 3, not 103. It is a 47.46 into 10 to the power 3, and then multiply by the 3500. This is basically the rate is given, so for per hour, and this is you can see the question that is given here. 35,000 kgs per hour, that is this rate, and the heating value is given at, for 1 kg it is a 47.16 46 10 to the power 3 kilojoules. So this is the total amount of the heat liberated, 1.66 into 10 to the power 8, it should be 8, slight mistake. Okay, so 1.66 into 10 to the power 8 kilojoules per hour, this is the total amount of heat liberated by the refinery of gases. So obviously our target is to find out R, means in this heat how much will be absorbed. This not the 100% of the heat is absorbed, only a portion of that heat will be absorbed, and that can be calculated by this equation. So now Q is calculated here. What is remaining here? Alpha is given here, the only the area alpha nu. So alpha nu is the area of the wall having tubes in front of it. Let us take how to calculate it. So projected area of the one tube is calculated by L by D. Simple, this is the projected area, 12 multiplied by 12 meter multiplied by the 10.5 centimeter means 0.015. This is meter square. This is the projected of one tube. Then there are total number of tubes we can find out, because total projected area is 150. So if you divide 150 divided by the area of the one tube, that gives the total number of tubes in that furnace in the radiant section. 120 tubes are there. And how we can find out? So we can find out simply by this equation. This is the number of tubes, okay, and this is the area of one tube, okay, and this is the space, because it is a 2 OD, so that's why you have to multiply by 2, so that we can find out the total net area of the wall in front of the tube, that tubes located at that position. So you have to multiply by 2, because 2 is given as 2 AD is the space provided here. So in this way we can find out the alpha a new value. So all these values are calculated. Now calculate the R value. It is comes around 44%. What it means, that 44% of the total heat is absorbed by the process fluid. Only the 44, means the remaining 56% is either it has to be go through the convection section, or obviously maybe some losses are there also. So now come to the Next part of this, how to find the temperature, it's a very easy one. We know that mcp delta T, that is the total amount absorbed. If the total amount absorbed can be calculated by sensible heat, that is the amount of heat absorbed. So m, mass of the material, is given, but that is 1200 barrels per hour, that is given here. So we have to convert this 1200 barrels per hour into kg. How we can calculate it? We know that 159 liters per barrel, this is a relationship to convert the barrel into the liter, and this is a relationship to convert the liter into the meter cube. And then this is a specific gravity into 10 to the power 3 gives the density in the kg per meter cube. So if you multiply the volume multiply by the density, that gives mass, kg. Then multiply by the Cp, 2.268 kilojoules per kg per degree Celsius. So mCp, and then this is a delta T, that is equal to the 44% means 0.44 of this amount, 1.65 into 10 to the power 6 kilojoules. This is the amount that is liberated per hour, and if you multiply the 0.44, that gives that this is the total amount that is absorbed by the process fluid. And then simplify it, you can get the delta T value as 188 degrees Celsius. So we know about heat inlet 220, and you have to add 188, that gives the 408 degrees Celsius, that is the temperature of the outlet of the petroleum stock. So in this way we can find out the temperature of the outlet of petroleum stock. So that is the calculation method. Now come to the second method for the radiant section, how to find out the working of the furnace, and that can be taken by the Lobo-Evans method. In the Lobo-Evans method, there are certain checklists to find out whether the furnace is working in the good conditions or not. So we are just going to check out these lists basically. So working of the furnace is checked by this method. It incorporates all the factors that influence the radiation section. To check the Lobo-Evans method consists of the following steps. So what are the steps? Number 1, alpha value, that convert the actual exposed surface to a cold surface factor is evaluated, that is the first step. Second step, area of the wall that carry the tube is evaluated. Third step, with the known factors of the known characteristics of the fuel and air fuel ratio, partial pressure of carbon dioxide and water vapor is find out. Then assuming the adiabatic flame temperature are equal to bridge wall temperature, tube skin temperature is find out. Then fifth one is the flame emissivity is calculated, and it is related with the partial pressure of the gases that is present in the radiant section, and the mean radiant beam length. What is the meaning of mean radiant beam length? L. It can be calculated how? Mean length of radiant beam is depend on the geometry of the furnace, whether it is a cylindrical or the box type. For rectangular type of furnace where length, breadth and height dimensions are in the ratio of 1 to 1 or 1 to 2 to 4, then we can find out the mean basically the radiant beam length L is equal to cubic root of 1 by 3 cubic root of volume of the furnace. So where obviously for the circular furnaces this L can be calculated as the 1D, where height is in many times of the diameter, obviously in the circular type of the furnaces. Then the next point, exchange factor is evaluated in terms of the flame emissivity and the ratio of AR upon alpha Nu. Value is calculated. Rate of heat absorption QR is given in the by RQ upon alpha Nu, and Q is assuming R a fraction of total heat release, and this can be calculated. So in fact all these are the parameters that you need to calculate for the Lobo-Evans method for finding out the working of the furnaces. So this is all about. Thank you very much.